Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video I will tell you about the data we are using in supervised machine learning. You should understand the structure of tabular data, which we are mainly using in this course. You should understand the difference between target and features, and the difference between labeled and unlabeled data, which is very much related to the concept of the target variable. And you should know the concept of the data generating process. As a toy example, we will use the iris dataset, which you perhaps already know. The task in the iris dataset is to classify iris subspecies. So iris is a flower and there are subspecies of that flower. In total 3 subspecies in this dataset. And of each subspecies, called versicolor, virginica and setosa, we have 50 flowers. So in total n equals 150 iris flowers, and the characteristics that describe these flowers are the sepal length, the sepal width, the petal length and the petal width. So we have 4 characteristics to describe these 3 classes of iris flowers. It's a very small data set. It's also a clean and low dimensional data set, which makes it perfect for visualizing things while teaching machine learning and statistics. But out there in the wild, usually data sets will be more complex and tasks will be more difficult to solve. But for this case, the iris data set should be okay. So the data in supervised learning. We have different measurements on n objects, and we divide them into the target variable and the feature variables. The target variable is always the thing that we will try to predict in statistics. This is also called response variable, for example. Could also call it output variable. And in the iris dataset, it just contains the class of these iris flowers, so setosa, virginica or versicolor. On the other side, we have the features, which we denote by x. We have, in this case, 4 different features with different entries of how long or width these sepal and petal things are. Usually we assume that there is some relationship between the features and the target variable. So usually we know the features up front. During training, we also know the target variable, but we do not know the exact relationship between the features and the target variable. And basically all of supervised machine learning, well, not all of it, but a lot of supervised machine learning is about learning exactly this relationship between the features and the target variable. There are different data types that apply both to the target and the feature variables. We have 4 types. Here, numerical variables are just real numbers. Integer variables live in Z, so they go from 0, 1, 2, but also -1 and -2. Then we have categorical variables. So this is just a finite set of different categories, can also be characters, A, B, C. And then last but not least, we have binary variables, usually denoted with 1 and 0. Sometimes we also encode this as 1 and -1, but we will make clear which is which when we get to it. For the target variable, the data type has a direct consequence on the task that we try to solve. We have regression and classification, and regression is always for numerical and integer variables, target variables, and classification is for categorical or binary target variables. Most of the learners we will cover only deal with numerical features. We will also see some learners like the tree-based approaches that can use categoricals without problems, but usually we need some encoding of categorical variables. Could say that the binary variable is already encoded as a real number, let's say 0 and 1, but for these categorical variables, C1, C2, CG, which could also be just characters, A, B, C, we need some encoding to numerical values, which I will show you on the next slide. And if not stated otherwise, we assume numerical features. How can we encode categorical variables? Let's stick to the case where we have three classes. For example, the output of the iris dataset. So in this case, K is three mutually exclusive categories called ABC, for example, lower here. And we want to encode this to a scalar vector of length K tilde. Okay, so K tilde can be the same as K, which is so for the one-hot encoding, but it could also be K minus 1, for example, for the dummy encoding. In any case, the output of this encoding will be a vector denoted with O of x, and all the entries of this vector are 0 and 1. So in the end, O of x will just be a vector, for example, 1, 0, 0, has 3 entries if K tilde is 3. This, okay, let's clean this up first. This here is the notation of OXJ, which means J as the jth category. This is an indicator function I, which is always 1 if x is J and 0 otherwise. So we could also say this I of x equals J is either 1 if x is J or 0 if x is not J. Okay, so now we have a vector O, and this is a numerical vector. We can just say each entry of this vector is a separate feature. We can just use this as before, or as we would do in any other case with numerical features as well. So now the question remaining is, how can we exactly do this encoding? There are several ways of doing this encoding. We will show you 2 ways of doing this. The first is one-hot encoding. It's called so because exactly one element is 1 or hot, which means in the example of x being something from A, so x is A, B or C, so the vector O of x has also 3 entries, so K tilde is same as K. And for an example of where x is C, we just put x C to 1 and all the others to 0. So in the end, we have O of x is 0, 0, 1, which is a numerical vector then. In the dummy encoding, we only say that at most one element is 1. To remove some redundancy, we will have learners that require non-singular input matrices, such as linear regression. And for this, we can't use one-hot encoding, but we can use dummy encoding. And the difference is that, first of all, in this case, we only have K tilde is 2. So we only have 2 values in this numerical vector. And if x is A, then the first element is 1. If x is B, then the second element is 1. But if x is C, no element is 1, and both elements are 0. So here in this example, O of x is 0, 0, which means we have the third category, also called reference category. And we can use this for encoding targets and features, doesn't really matter. For some features with a natural order in their categories, we can also use encodings that reflect this ordinality, for example, a sequence of integer values, but we will return to this when we need it. Very well, let's speak about the term labels now. We call the entries of the target column. Okay, so the target column is this Y column, and the entries of this target column we call labels, which also means that we can differentiate between labeled data and unlabeled data, where labeled data is everything where we do have labels, and, well, obviously labeled data is where we don't have the labels. I guess that is pretty straightforward. Usually we will use labeled data for training a machine learning model, and at prediction time or at test time we have unlabeled data. We only know the features X, and we have to predict somehow the unknown label. Let's fix the notation for data. D is a data set, and D consists of tuples, in total n tuples, and each tuple is one row of the data set consisting of the features x of observation 1 and the target y of observation 1 in the first row, and then in the other rows the others follow. The data set lives in this space here. Let's unfold this a little bit. So let's start with x. X is the input space. Usually we say we only have numerical features, so the input space would be a subspace of r to the power of p, where p is the number of features. Okay, and if we have categorical features, then we encode them first via dummy encoding, one-hot encoding, and then they are numerical features as well. Y is the output or target space, and one observation, so the ith observation, is denoted with x, I, y. I. Please make sure to at least note the difference between subscripts and superscripts here. So if we have a superscript, like here, x, y, then this means this refers to the ith observation, so row in the data set. And if we have a subscript, j, like here, xj, then this refers to the jth feature vector, so to the column of the data set. Of course, the entries of these columns or rows then need both superscript and subscript, as in this example here. Okay, if we put together feature space and target space and take it to the power of n, then we have the set of all data sets of size n. The set of all data sets of size n, and we denote this by dn. And if we take the union of this thing here over all n, all natural numbers n, then we have the set of all finite data sets, and we call this D without subscript. So we have n objects described by p features. Now that you know what the data looks like that we observe, let's speak about the different thing, the data generating process. Of course, there is a connection between data generating process and observed data, which is that we assume that the observed data was generated by this data generating process. So by some probability distribution, p, x, y, which is the joint probability distribution of features and target, so defined on x times y. We denote the random variables also by lowercase x and y. So in some literature, perhaps you will see the difference in notation between capital X referring to random variables and lowercase x referring to observations of those random variables. We don't do this here, but we will make sure that context makes clear if we are speaking about random variables or about observations of those random variables. So the data generating process is the cornerstone of machine learning. So if we would know the true data generating process, everything would be very fine. We could just use this to predict a target given features. But usually we don't know this, so learning this data generating process or this joint probability distribution is more or less everything what the machine learning is about. We assume that data are drawn IID from this joint probability distribution. IID means independent and identically distributed. Let's unravel this as well. The first I stands for independent, which means that different, let's say, rows of the data set are mutually are drawn mutually independent. So if I know row I don't know anything about row I plus 1 or I minus 1. Right? So these are independent from each other. This does not mean that we assume that features and target are independent from each other, because, well, if they would be independent, we could not predict y very well from x, right? So of course there is some structure going on, or hopefully there is some structure going on that we will learn, but the rows of the data sets are drawn independently. This is of course different, for example, for time series, but we will not treat this here. The other I means identically distributed, which basically means that all these observations are drawn from the same data generating process, pxy. It's a strong assumption, but also a very crucial assumption. It's not always realistic. As said, for example, for time series, we need different assumptions, but we focus on the IID scenario here. Now, let me quickly explain you what these two figures here mean, why we have included them. So let's start with the left figure. This could be the joint density of x and y. If x is just one numeric feature and y is one numeric target variable, then this could be, for example, a bivariate normal distribution. And we could say, well, that's the data generating process. We can now sample from this data generating process and get data points, these orange dots here, which we can plot, x versus y. And we can, for example, do a linear regression here. So this black line here could be the linear regression line. And we can then use this linear regression to predict new y values given new x values. So perhaps you're thinking now of linear models as described like this. So y given x is Gaussian with some linear function of x as the mean and some variance sigma square. And what we have on the left hand side is the joint distribution on y of y and x, and here in the linear regression we have the conditional distribution of y given x, but of course together with the distribution of x we can also infer the joint probability distribution, and we'll see later more on that. Some final remarks here. As I already told you, so we write random variables with a lowercase, and context will make clear when we mean random variables and when we mean observations or function arguments. Distributions can be characterized by a parameter vector. We could then write the joint, for example, a density function of x and y given theta with this pipe operator here. But usually in this lecture we take a frequentist perspective, so not a fully Bayesian perspective. So we still use this pipe operator because we think it proves legibility, but that does not necessarily mean that we condition on theta in a strongly probabilistic Bayesian sense. So we could also use a different notation. So instead of p of x given theta, we could also have p of x with a subscript theta, or just comma or semicolon. But as this notation makes it very easy to switch to Bayesian view, we prefer this notation here.